The electromagnetic flow meter, commonly known as the magmeter, gets its name from the magnetic field generated within the flow tube that produces a signal proportional to flow. This principle employs Faraday's law of electromagnetic induction. Magnetic flow meters are built so the direction of the magnetic field is perpendicular to the flow, and the line between the electrodes is also perpendicular to the flow. As a conductive liquid flows through the flow tube, an electromotive force is generated. The electrodes detect the electromotive force. The electromotive force is proportional to the flow velocity, flux density, and the meter inner diameter. The flux density of the magnetic field and the meter's inner diameter are constant values. Therefore, the magnetic flow meter can calculate the flow velocity and volumetric flow from the electromotive force. The basic components of the magnetic flow meter body are a lined flow tube, typically Teflon, excitation coils, and two electrodes mounted opposite of each other within the flow tube. Current is applied to the coils in the magmeter to generate a magnetic field within the flow tube. As a conductive fluid flows through the meter, an electromotive force is generated. This force is detected by the electrodes, and the resulting value is converted to flow rate. When magnetic flow meters were originally designed over 50 years ago, they utilized AC-type excitation. AC-powered magnetic flow meters use line frequency to generate the magnetic field. The frequency of AC excitation is typically 50 to 60 Hz. This type of excitation has a very fast response time, making it suitable for slurry applications. The weakness of AC-type excitation is that it has an unstable zero, and the accuracy is a percent of span as opposed to a more accurate percent of reading. Because this type of excitation uses line frequency, the power consumption is also very high, making this an expensive meter to operate. In an effort to improve accuracy and reduce energy cost, pulsed DC-type excitation was introduced several years later. The average excitation frequency is between 3 to 8 Hz, but can go as high as 30 Hz. The major benefits of pulsed DC excitation over AC excitation is the improved accuracy and zero stability. The accuracy of a DC-type meter is a percent of reading. This gives you a more accurate measurement throughout the entire measuring range. Unfortunately, because of the low frequency, the response time is very slow, making it a poor choice for noisy applications. To overcome the disadvantages of the standard AC and DC excitation methods and keep the advantage of a high signal-to-noise ratio, Yokogawa's patented dual-frequency excitation is the ideal combination. Dual-frequency excitation combines the positive benefits of both AC and DC excitation, using both a high 75 Hz frequency and a low-frequency excitation of approximately 6 Hz to drive the coils. Dual-frequency excitation is an innovative method that superimposes high frequencies on low frequencies and utilizes the advantages of each while eliminating the previously discussed disadvantages. The combination of these methods results in the flow noise immunity and fast response of the high-frequency excitation method and the high zero stability of the low-frequency excitation method simultaneously. The dual-frequency waveform can be observed by putting an oscilloscope on the excitation terminals of the Yokogawa ADMAG magnetic flow meter. You can see the low excitation of approximately 6 Hz, the high excitation of 75 Hz, and the two signals superimposed on each other. The superior advantages of Yokogawa's dual-frequency excitation makes the ADMAG series of magnetic flow meters essential for your process needs. From the most basic to the most extreme applications,